Oh, somebody was just in the middle of asking me something, right?
You're going to give us the answers to these.
Yes, so I have the answers for that. I'm going to sit on them for a little while.
Okay.
Oh, yeah.
I'll give them to you in a bit. Yeah.
36 from 2.7.
There we go. Oh, and there were a couple of, let's see, this. I think this is one of them. Maybe not. Oh, yeah, so we'll see if somebody asks a question. There are a couple from yesterday I said I might do today. 36.27, the one with the tangent?
Yeah.
Oh, okay. So this one's a little weird. There's not real work to do. They just want you to identify the parts of it. So, alright, so remember there are two main forms for finding the derivative or the slope of the tangent line. So those mean the same thing. Of any function at some point. One of them looked like this. And there you can really see the y2 minus y1 over x2 minus x1, right? And the other one looked like this. Oh, you know, there's A in here. Just make it more specific. Bam. Right?
Oh, so that's what I was supposed to do?
So which form, so really all you got to do, what they ask you for number 36 is each limit represents the derivative, and that's what these are, right? These would both be f prime at A, f prime at A. They both find the same thing, just in slightly different looking ways. Each limit represents the derivative of some function f at some number A. State what f is and state what A is. That's all you got to do. So what would f of x be, and what's A?
Here's one. Isn't it 1?
Nope.
8, wouldn't 8 be pi over 4?
Yep.
And
What's 1? 1 is f of pi over 4, right? 1 would be f of pi over 4. You see, they can just relate that form to that form. Do you guys see
isn't that
that?
0 over 0 though? So like, wouldn't I?
Of course it's 0 over 0. I'm hoping we see enough of that. Some of you guys, alright, 0 over 0 is one of the main ideas in chapter 2. Because we're trying to do something that was impossible before we brought limits. We want to find the slope at one point, which is impossible. So if you look at that, that's 0 over 0. If you realize this, it never gets to that.
It gets to what, 2? Or?
Gets to 0 over 0. Because what's the only time this is 0 over 0? When x equals. But this, does it ever let that happen?
No.
That's the big idea. That's the calculus step to take. Or one of them. Anyway, is I can find the slope at a point by getting as infinitesimally close to that point as possible, which is what that accomplishes. Maybe. So now I've lost train. Oh, first thing is, what shape is it in? It's in this shape. So then I can identify what f of x is. And 1 is f of a. So what's f of x? And just to double check, what's tangent of pi over 4? All right, kick ass. Right, and then x minus a. Cool. So you can identify f and a relatively easily. So this is just backwards. So normally, that's all I wanted. Yeah. Just to make sure you understand what that format means. It's good news, right?
Yeah.
All right.
I just want to help with 36. I mean 32. 36.
In the same section? Yeah. Oh, okay. All right. When I have polynomial stuff, it becomes relatively easy for either one of these. Then it's all about either factoring or foiling and canceling, right? The minute I don't have polynomial stuff, it can get very weird. This is like one step away. This problem is a radical. And then it's another step away because the radical is on the bottom. These problems are all about how organized are you, and do you feel comfortable with radicals and how to deal with them. So, the process to set up the problem is always the same, depending on which form you pick. So this one says, find f prime of a. This is number 32. Says f of x is 4 over rad 1 minus x. And I want to find f prime of a. Band practice. What is happening? So then, what? So I just put two forms up to find this, right? Which form do you guys want to use? You want to use the x to a or the h to 0?
H to y.
Sure, let's try h to 0. I like it. I'm open to either one. So then I'm going to choose this format, h to 0, f of, what's the general idea? A plus h. Good. y2 minus y1 over x2 minus x1. A's cancel, that's why there's just an h from the bottom. Cool. So to find the derivative, since it is the slope, I'm building it off the slope that we know. It's awesome. It's almost too much to really believe. y2 minus y1 x2, that's what all this is. Just when I bring this into play, that's the calculus step. That's when it becomes calculus. So now I just plug and chug. Limit h goes to 0. What does that look like?
1 minus a.
Who to what?
Minus a. 4 over radical 1 minus a minus h.
I like it, because you'd have to distribute the negative through. Stop there for a second. This already looks so promising. That's why I kind of like that you picked this way, because that's the way that looks a little grosser. Minus
4 over radical 1 minus a.
All right, cool. Almost in stereo. I like it.
Can't you
All
just
over
bring
it.
the radicals down to the h?
You wish you could.
No.
Hell no. So,
This isn't multiplying 1 over h?
sure.
So, like,
So you could bring the h to both of these.
Yeah.
You just can't bring these down
and
somehow.
then you just LCD. Or,
Okay, sure. You could do that. Yeah.
that's all.
That's one way to do it. Sure.
How would
Yeah.
you do it, Jeff?
Yeah.
I would. Well, I mean, that's the way to do it. That's the way to start with this thing. Is these are two fractions, right? And where's the problem really? If I try to plug in a 0, what happens on the top if I plug in a 0? That's the same as that, right? So 0 minus 0 over 0. So there is a problem there. And there's a real quick check to make sure that you set it up correctly. It has, when you're finding the derivative this way, it has to be something like 0 over 0. It has to be that, because that captures the idea. All right. So, sure, yeah, totally. You could split this h. It's both of these being divided by h. So you can just put an h down there, right? And then you can get an LCD and go from there, yeah, of course. So what would the, so let's just do that. So we got limit h goes to 0. 4 over h square root of 1 minus h minus h minus 4 over h square root of 1 minus a. Why not?
And then multiply by.
So what does this guy need?
1 minus.
Square root of 1 minus a. All right, so now we're just doing LCD, right?
Yeah.
He needs that. He needs that.
And now can you multiply by the conjugate?
Well, let's see what we get now. Let's clean this up a little bit. There's not much we can do anyway. So you get the limit. H goes to 0. 4 square root of 1 minus a minus 4 square root of 1 minus a minus h over. So let me see if you guys can deal with this.
Yeah. Start with
Right? 4 on top, h on the bottom. And so the bottom is going to be square root of 1 minus a minus h square root of 1 minus a. Yummy.
Can you multiply by the conjugate or not?
Can't just like redo.
That's what I did.
Yeah. Because you still have the problem, right? When you try to let h be 0, this is still 0, and that's still 0.
Yeah.
So the problem's still there. You got to keep going until you kill the problem. Don't stop here and put a 0 in and go 0 equals 0, and I have too many people telling me that somehow that's infinity. That is just as valid as saying it's 0, because they're both wrong. It's not 0, it's not infinity, because they're against each other, right? They're working exactly against each other. So yeah, when you have radicals in here, that kind of tells you conjugate is going to possibly be used more than likely. Yeah. So let's see, the limit h goes to 0, 4 over h. So what would the conjugate be?
1 rad, 1 minus a plus 4 rad, 1 minus a.
Yeah, so rad 1 minus a plus rad 1 minus a minus h. Rad 1 minus a plus rad 1 minus a minus h. Fake sympathy. Oh, I'll get used to it. This is nothing. Look at that. That's barely a full board. Give me a break. When I start needing to have whiteboards installed around the room, that's not enough sometimes. So then you can maybe start to continue to be quiet. So. Sorry. What do you get when you multiply the top? This is nice.
Yeah, 1 minus a.
1 minus a minus 1 minus a minus h. Let me stop there for a second. Now let me just stop here. Really, really good stop. Everything I've done so far is nothing that's anywhere near out of the reach of any of you, or should not be. And what's been motivating me every step? I was indeterminate form here, so then I step back and say I've got fractions, LTE is a really good idea. I got radicals, conjugate is a really good idea. I have these ideas of what to attack it with. If I attack it and it doesn't bring me somewhere good, and I feel good that I did the work right, I step back and say, what else could I try? But normally, there's not a lot you got to try. It's not like trig identities where you're like, I'll try this, I'll try that, I'll try this. Oh, shit, nothing's going fine. There's like almost only one thing you could do most of the time with these. So that's the top. On the bottom, I'm not going to remember. Just don't. Is that plus that. Whew. So what happens on the top there? Yeah, the 1 goes away, the A's go away, minus and negative is plus, and the H cancels. So the problem died. The minute the problem dies, you can plug a 0 in because you killed the problem. You killed the reason. The reason you couldn't plug 0 in just died. So now I can plug a 0 in for H. Stop there for a second. You guys see the idea? Yeah.
So the only time where we actually have to keep going is when it's 0 on top of 0?
Exactly. That means you haven't done enough of the limit yet to determine. That's why I love the name indeterminate. If you go, it's still 0 over 0, that's still indeterminate, I got to get a freaking answer. I have to determine what the answer is. I haven't made it look right yet. Now I killed the 0 over 0 piece. It's gone. So now I can plug a 0 in. On the top I got 4. What do I get on the bottom here? Square root of 1 minus a minus 0. So square root of 1 minus a times square root of 1 minus a
Is 1
1 minus
minus a.
a times square root of 1 minus a plus square root of 1 minus a is 2 square root of 1 minus a, right? Oh, so yummy. So let's see. Can you guys simplify that even more? Let me see if you guys... Oh, let me put it up here.
So 2 over 1 minus a times
Right, Elizabeth? Now watch this. I'm going to blow your mind. You ready? You ready?
2 over 1 minus
What's the power on this 1 minus a? What's the power? 1/2. So you got 1/2 of a 1 minus a times a whole 1 minus a is 1 minus a to the 3 halves. Kick ass. I don't know. Oh, square root of 1 minus a plus square root of 1 minus a, because that went to 0. Yeah. So you get 2 over 1 minus a to the 3 halves. Yes, sir.
Wouldn't you usually try and get rid of the half of the square root multiply the 1 minus a to both sides, to the top and bottom?
No, not necessarily. You're trying to rationalize it, but there's no real big reason to do that here. I know you're used to doing that, but there's really no reason to do it here. Just introduces extra crap you don't really need. If it was 1 over square root of 7, then yes, rationalize that. This is a function. If I plug a number in, maybe I don't even have a radical at the end, so I shouldn't rationalize until I know what the number is. Does that make sense? A little tiny. Notice this. What did this basically start off as? What is 1 over rad x? It's kind of the form of this, right? This has been shifted and it's multiplied by 4. Who gives a shit? It's basically 1 over rad x, which is x to the negative 1/2. Kick ass. And this basically ended up being x to the negative 3/2. So some of you guys that are desperately hoping someday you'll be able to use your shortcut rules, that should sound very familiar.
I think we lost a negative sign.
We could have.
Because this is supposed to be negative.
No, it's not.
It's not?
No. Because chain
yeah,
rule,
maybe.
shit.
Oh, okay.
Okay, sorry. No, I'm sorry. So again, it's nice if you know the rules, but yeah, you gotta be careful. All right. So this is not a lot of work. This is not. This is a nice little tiny problem. Believe it or not. Oh, and it's making you feel so much better for what's in your future. I know. The nice thing for you guys is I'm talking about relative to all of math. This is a little tiny problem. Relative to this class, this is kind of a longer problem. Sure. Because we will get to the point where we can go straight from there to there in like a couple steps. Yeah, we're not there yet. Too bad. All right. Is there anything else from homework or from, it's wide open, whatever you want to ask.
2.633.
Oh, okay, good. All right. So you guys got what you want up there? More than you ever wanted? Okay. What was it, 33? I'm just going to write this the way I'm used to it. I always hated the arc crap. So when you see arc tangent, I don't know, it depends on the teacher you have for pre-calc. I normally stayed away from the arc. And I understand why they brought arc tangent, arc sine, because this looks like it's 1 over. But it's really the inverse tangent, right? They're totally different ideas. But I'm a true mathematician. I want to write as few as symbols as I can. So this is, how do I do this? So why do you think this is squeeze theorem? Who said that? All right. So why do you think this is squeeze theorem?
I don't know. It
I like
sounded
it.
right.
I don't know if I'm confusing myself. Isn't the boundaries between the ranges between negative pi over 2 and pi over 2?
Okay, good. That's
So
even better.
It's approaching pi over 2?
Yes. So, and the thing you have to be careful about is you're talking about this function, which I hopefully, in a way, that's almost silly that I just said that. You're like, there is a difference between these two functions, right?
Yes.
But here, if I let x go to infinity, then this is going to go to pi over 2. You guys remember that? Mm-hmm. So tangent looks like around in the asymptote, the negative pi over 2. So if I invert that, now the asymptotes will be at pi over 2 and negative pi over 2 like that, right? So if I let x go to infinity for tangent inverse of x, then it's going to approach pi over 2. But that's not what I have. But why is that not a big deal? What is this thing doing when x goes to infinity? This thing is going to infinity. So it's going to end up doing the same thing it would. Yes, cool.
So it's just pi over 2, right?
Yes, but tell me, flush it out. As x goes to infinity, e to the x goes to infinity, right? And then you can say, well, as the input of this goes to infinity, its output's going towards pi over 2 because I know the shape of it. That's beautiful. The more you know, the less you have to do. But you're still going to show me something or say something, yeah. So we've talked about that before. So now I understand why you said squeeze theorem, because I said the arctangent might show up sometimes for the squeeze theorem, but that's when it's multiplied, by something else, or it would be like this probably. As x goes to 0, this would have a bound of pi over 2, right? So you could bound it using the squeeze theorem, but does that make sense?
Yeah.
Okay.
If we get a quick review of symmetries, the only one I can remember is like cubes have that symmetry about.
Oh, all right. So, yeah, because there was like 4 questions, and just about everybody I've graded have circled it and said work, and some of you guys are like, yeah, man, stop saying that. Without work, I can't do shit. I mean, I've got to see work. And if it doesn't say use the calculator to get your answer, do not use your calculator to get the answer. Right? That's no good. So the main types of symmetries that we know at the moment are just 2. We know even and odd. So we're going to learn some more symmetries eventually. And to be even symmetry, I just remember it's like x squared, which makes sense because it's an even power. So when I plug x in, I get f of x out. What do I get when I plug a negative x in? Same thing. So the test for the symmetry, for each of these actually, is if f of negative x equals f of x, it's even. Right? So I plug a negative x into the function. If I get the same thing back, if the negatives somehow cancel, then the function, the whole function itself is even. Odd, of course, I remember like this, right? Which is normally considered through the origin, it's symmetric, right? So x goes to f of x. Where does negative x go? Negative f of x. So if f of negative x equals negative f of x, that's odd symmetry. Right? So that's the work you show me. Yeah?
So are you saying that for the odd it has to be the same sign and for the even it has to be the opposite sign?
Yes, so for example, if I had, what's the one on the practice test? Oh, blah, 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 blah. Here we go. So if I had this yummy function here, so 3 6th root 4 minus x squared. Right? So you can argue that you don't have to show much work, but you got to say something. So if you want to show the work, what is f of negative x? It would be 3 6th root of 4 minus negative x squared, right? Is that cool? Just plug a negative x in. Of course, what immediately happens there? 4 minus negative x squared is just x squared, right? The negative dies. Is that the same as it used to be? Yes, so that equals f of x. So what kind of symmetry does that have? Even. Which is kind of obvious because, of course, that's itself has even symmetry, right? Cool. That's all I'm saying.
Okay.
Yeah. So, and most functions that somebody just makes up out of nowhere will not have either of these symmetries. Of course, you learn about stuff like, this parabola is not evenly symmetric. It isn't, because it officially is not centered at the y-axis. But it has its own freaking mirror, right? It still is symmetric. It's just symmetric around x equal a, whatever the hell that is. Do you guys remember the axis of symmetry? Right? The axis of evil's cousin, I guess.
Could we also go over the epsilon delta question?
Sure. Was that in the middle? Is that... Everybody's got that up there? All right. Okay. What about which epsilon delta?
Problem 7 on the practice test.
Oh, okay. All right. Well, I mean, let me do this. I'll go ahead and give you the answer key. I don't like to hold on to it, so I force you guys to stay, but you can leave if you want to. Here. I'm like, I don't want to redo it. I already did it. Here it is. Make sure you have a front and a back. My prayer was really messing with me. I don't know what's going on. Just showing the kids a movie. Nobody told my team just to show you guys movies the whole semester. Yeah. So it's on the back, number 7. I sort of tried to write these. And I gave really quick answers. Okay, so in the homework there was, and I think we even looked at this, and I'll come back to that question. You still have a question on that. Number 7. What was it in the homework? It was find the domain of, it was this here, right? If I remember correctly. So the official way to do it was to factor this, and then you can make a little number line. You just can't graph it and give me the answer from what you see on the graph. I wanted to know, do you know how to do this by hand? That's the important thing, right? So you could argue, do you know what that looks like? I mean, you could, without using a graphing calculator, you know this is a down parabola at 16. And they can say, if I can find the intercepts, I know where this thing is good, because it's got to be the positive parts, right? So you guys just didn't show me enough work sometimes. -2 to 2 showed up, and I'm like, where the hell did that come from? Tell me something. So even if you graph it, you shouldn't have to graph it to know the rough form of it. And to get the answer for the domain, you don't need a is that perfect? If you gave me this, and I had asked you to graph it, and you gave me this, then that's shit. Hey. But to figure out the domain of this, I graph and I go, oh, I just need what those are, and this is where it's positive, and it's got to be a positive number. So then it's between those two, and then I can find those intercepts, and bam, there you go, done. But I need to see that at least. Or you can do the work, break it up, make a number line, see where it's positive, negative. I think it's the way I showed you in class. One of those two. You got to show me something. So this problem is even easier. I forgot. Which one was I looking at? 7. Oh, no. 7. We can look at 7. But like number 2, I just want to say this real quick because I didn't really show much, but that's because I think the function was, I gave away all my practice tests. What was a function? What was the F function? Oh yeah, it was this one. So this interior's got to be positive, right? So to find the domain, this can't become negative. So I need to find out when is this positive. Well, I know it looks like this at 4. So we're going to find those two intercepts. And of course, the intercepts are just 2 and 2. Negative 2 and 2. Right? So I didn't really show enough work for me. But that's the answer key for the answer, at least. Right? So you got to explain to me what the hell's going on.
So for the work, do you want us to just graph it and show the 2 points that we're using?
Yeah, you can say, right here, you just say, the inside got to be positive when, and then you can do the work, you can show me the intercepts.
Okay.
Between them. Yeah, beautiful. That's all you got to do. Beautiful. All right, so coming back to 7, and now that you guys have the, so I tried to show you exactly how I want to see it. Side work on the side. Even box it off. Have it way over there, right? Don't look behind the curtain, blah, blah, blah. And then you do the proof basically just in reverse. Let delta equal epsilon over 3. I mean, are you guys kind of with me? And again, to point this out, I don't think I've said this directly except to one of you guys, but what's the slope of the function on number 7? It's a linear function, right? What's the slope? -3, so its absolute value is 3. And notice what I have to divide epsilon by 3. So if it was -4x, blah, 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 it'd be epsilon over 4. So you can kind of, you know what to expect for your epsilon. So linear functions are just so simple to work with. But of course, we want the proof format to be the hard part, not the function itself to be the hard part. Yeah?
Can we go back to one from 2.4?
Yeah.
Number 36.
All right, there you go. There we go. All right. So we worked this to a point, and just let's remember. So we want to show this. Of course, you know, I took a class where I had to prove that the square root of 4 was 2. Or even I had to prove 1 plus 1 is 2, for example. So I understand the frustration when you're like, I got to prove this shit? I just put a 2 in there and done. So the whole point of the problem is not, I'm showing you a better way to figure that that's the answer. this is introducing you to a proof format with an easy problem. So don't, if you don't get it, sorry. Because I understand, like, I'm not like, there's just one out. Of course it. So we're getting used to the proof format with an easy problem. So I know this is true. So what do I need? I want to show when given epsilon greater than 0,
x minus 2 absolute value of x minus 2.
if x gets close to 2, if my inputs get close to 2, and close is defined with delta for x's, then my outputs, let's be specific here, Jeff, get really close to 1/2. And of course, closest for outputs is defined by epsilon. Sweet. So that what this really says is when my inputs get close to 2, that's what close is defined using, then my outputs get close to 1/2. And the closest is defined by epsilon. Alright, maybe. Alright, cool. So that's what we kind of want to show. So the side work is where we started and where we got lost a little bit, right? And there's there's an example just like it. Well, it uses what we need. Example 4 uses what we need. So I'm going to show you now, because this is one of the weirdest problems on here. So the side work we started with, how do you start the side work? And of course I could have been more specific
1 over
here.
x minus 1/2.
Yeah. So start with where you want to end up for the proof. I want that to be true. And we got to the point where we got like denominators. We put these together, so we got 2 minus x over 2x. And a lot of you guys wanted to multiply that up, but that makes no sense for several reasons. So what I do instead is something that doesn't feel very... since this is an absolute value, I can turn those around.
X minus 2.
Is that cool? Because it changes the sign, but the absolute value makes it always positive. Who gives a shit? So the absolute value of a minus b is the same as the absolute value of b minus a. Because the only difference between them would be a sign, but the absolute value strips the sign away. Alright, we stop there for a second. That's as far as we got the other day.
Are they multiplying each other now?
Yes. Yeah. Alright, so what example 4 introduces,
changing it to c.
when I have a part of my expression, here's what I want, and here's extra shit. So here's the thing about inequalities. What I want to say, let me really focus on this. And to tell you honestly, I just realized I'm going to do this, and I'm going to go relatively quickly because I'm not going to give you one of these on the test itself. I'm sorry. I might on a bonus. I always give 3 bonuses on every test. So that I'll probably make one of the bonuses something like that. But real quick, I want to be able to say that that is less than something, which I can then set less than epsilon. And then my inequality is still good. It still holds. All right. So here's what I'm going to do. What am I doing with x's in this problem? I'm letting the x's get close to 2, right? So let's just pick an easy area around 2. What's the easiest little area around 2 I can use? 1 to 3. Kick ass. And this feels so much like cheating. But a lot of proof things feel like cheating. So if I look at 1 to 3. So x equals 1, 2x equals 3. What is 1 over 2x between those? So at 1, what is it?
1/2.
Yeah, so at 1 it's 1/2. And at 3 it's... So on this interval, 1 over 2x is between those 2 values, right? Let me stop there for a second. Let me let you absorb. Absorbing, Jeff. Nothing. There's a comma there. It's not weird. I know what it means. All right.
We're going to solve for that.
Now, here's what's cool. So that means, obviously, now why does the absolute value not really matter on this? Because my x's eventually will have to be positive because they got to get close to 2, right? So that means, let me see if you guys cool this. 1 over 2x will always be less than 1/2 as I get close to x. Because if I get even closer, it's going to be even smaller than 1/2. you guys see what I'm saying. Because, maybe you see what I'm saying. Because if I get closer, I get 1.5 to 2.5. This will be 1 over 1.5, which is... Alright, maybe you guys see what I'm saying. So, I can let this be less than... So this is true. This is less than 1/2 times x minus 2. And then I keep going, so this is x minus 2 is less than 2 epsilon.
Why'd you use the bigger value?
I don't know, to be honest. What did I do?
Why didn't you use...
Oh, because I have to have something where this is always less than. I need this to be less than a value.
To be epsilon, so
Yeah.
we could almost pretend that that less than sign is an equal sign to the epsilon.
Well, it's even better just to realize it is a less than sign, so whatever I put here, this has to be a true statement.
Right.
So the only thing I changed from here to here was this. And 1 over 2x is less than 1/2 on that interval. All right. So if you look at example 4 in the book, you'll see it's a very different function they're using, but at one point they have to come up with some value to replace this with. And the reason I'm allowed to do that is because I know what x is going to do. So I have a little flexibility with what I can let it be. So look at that example. That's all I want to say about that, because I'm not going to...
So you take the interval between 1 and 3, and then you pick the value so that it will be less than it at a smaller interval?
It adds a lot.
Yes, as I get...
Yeah.
Yeah. Okay, maybe.
I think.
As I get closer and closer to 2. Yes.
Okay.
Cool. I like it. Yes? Not really. No, it does help that this function is continuous. I mean, that you know, you'd have to, if you really got into the deep technical parts of this, you have to address that. But most functions we're going to look at are nice on their domain. Yeah. All right, that's enough of that. That's all I'm going to say. So if you look at example 4, I think it was, right? Mm-hmm. And you can kind of compare that to what I just did and see how they're very similar.
Well, how would you prove that when you go backwards?
So now you let delta be this. And you basically follow this exactly backwards.
Okay.
Yeah, it's kind of nice. The nice thing is when you have to do something weird here, it's telling you you're just going to do the exact reverse to get back. Which is really nice. And I think they do that in example 4. I think they do... Do they show it all the way? Yes. Cool. There you go. They show it all the way on example 4 getting back. Okay, let's focus on what's going to actually be on the real test. That's enough of that problem. Anything else? Where we want to go next? There will be one epsilon delta proof on the test. There might be one in the bonus questions, like I said, but it will be pretty much, very much like this. So really, it's just a test like it's supposed to be. It's a test of, do you know the format of the proof? All right, I'm not going to give you some, holy crap, I tell you.
Mainly it's gonna be like limits.
Oh yeah, you know it's the biggest chunk of it's going to be limits. And pretty much the practice test, they try to make it mimic the weights of things. There's going to, you know, it starts off with the chapter 1 review kind of stuff. Then you got limits, and then you got derivatives, right? Finding the slope, and then finding the tangent line using a slope, right? Like number 9, referencing number 8, I think, if I remember correctly.
So let's check it again. You want us to, for derivative, you don't want us to, you can't use the shortcut.
No, no.
Okay.
You can only use what you officially know in the class you're currently taking. So we don't know shortcuts yet. Yes?
3C, I ended up getting to a point where I couldn't get rid of the problem.
Oh, and that's sort of the point. And is there really a problem? So 3C looks like this here, right? That's how it starts off, right? Okay. Is there a problem? So what do I mean by get rid of the problem? The problem would only exist if there was an indeterminate form. That tells me I cannot determine the answer. Is this an indeterminate form? No. What form is this in?
It's bigger than
Yeah, it's negative 2 over 0. Yeah. So what did I say? Why did I say positive infinity, Jeff?
I think I said positive infinity.
No, I said positive infinity on the yes.
Addition 0, negative 2. Oh, is it because it's going from the right?
Oh, it depends on what these are doing. That's right. What did I try to do? Oh, I tried to factor, but I don't think that's factorable. I can't remember now why I did that. So if you try to factor this, that is factorable, isn't it? But I don't think it cancels with that.
It does, but...
Is it? Okay.
Yeah.
I don't know why I gave up on that then.
I think it's...
Yeah, what would this be? 72, 8, and 9. So 8 and 9. And the 9's got to be positive. There. So minus 8 plus 9. Cool. How's that? Is that cool?
Yeah.
So then this part goes away. That's not the problem. But the nice thing, so what do I have now? I got 1 over these, right? Let me keep this written down. So I didn't cancel a problem. I just made there be less shit to look at to figure out, because this thing is really weird to figure out what's happening as you approach 0 from above. Is this negative or positive? I know the top is negative, but what's the bottom? I don't know shit. Well, now it's easier to look at. As I approach h from above, meaning I plug positive numbers in for h and they're just getting smaller and smaller. Are you guys with me?
Yeah, that's good.
All right. So then this is going to go to positive. The values are always positive. Are you with me?
So even if there wasn't like an indeterminate, we still have to go through all the stuff until you cancel it.
Well, if there's an indeterminate, you have to.
Well, yeah, of course.
If it's determinate, the only reason I did anything here was just to see if it's easier to look at, so I can figure out if it's negative infinity or positive
If
infinity.
we did it the other way, just plugging in the zeros and getting negative 2 over 0. Without
Do it. Say again.
If we just did plugging in the 0 and then getting the negative 2 over 0.
But this would lead me to believe it might be negative infinity.
Okay.
When actually, this is probably negative for every time you plug in something close to 0 from above. So if you try to plug in 0.1, this is probably negative. It cancels with negative on top, and that's why this is easier to look at. I can see that this always is positive. So it's going to positive infinity. So if it's infinity, you got to tell me which infinity. You want to be very clear on which infinity it is.
Yay!
All right. Our first test. Yes. Plenty. Can't wait. I made it really hard.
This one is like the first one.
Yes.
I did, what I did is when the book was on the computer, I did that.
Oh, shit. That explains that.
Yeah, that's why it looks like
Oh, man.
yeah.
Yeah.
I did it before class even started.
I got you.
Yeah.
I got you. Yeah, okay.
So it was a different, yeah, it was completely different. It was the wrong book.
Oh, okay. Yeah. Right. Yeah, but you have until the final exam.
Okay. Yeah. All right. Yeah, okay. Thank you.
Sure. Oh, yeah. Thanks.
Professor, as far as WebAssign goes, we can do it on WebAssign.